stream, aren't we? And we are streaming now. Okay, so good morning, David. The floor is yours.
Okay, thank you. Do we have students now on the Zoom online? We do have, right?
Yes, we have about close to 30 now. So
hello,
20.
we are here.
Yeah, okay. I would like to get small feedback regarding my yesterday's recorded presentation, whether you have solved the homework I've given. So if you could raise your hands, how many of you have solved the homework I've given you yesterday? Oh, at least I have one person who solved it. Did you manage to get a solution right? Did you get something out of it? You know what the solution is?
Actually, I have saw that presentation last year. So, and then,
okay.
So I already knew the solution.
Okay, but did you manage to solve it value for value?
I'm not sure actually, because I'm not considered the whole solution. Like I just watched the presentation, the theoretical part, because I saw this the same presentation. I did not do the exercises.
Okay, okay. I did not see the other people raising hands, so I will give you now a hint to how to solve, and I'll not show the solution. If you manage to solve it, you will get something. You will know whether you have done that or not. Okay, so let me start the presentation. Okay, so I had the other presentation done for you, but I lost it somehow, not for the second lecture that I have. So now I'll have recreated it very fast. So what I'm trying to talk about today is tomography. And yesterday's lectures, I wanted to show what is the main difference between planar imaging and tomography. And hope you have understood it well, that there is a difference between a set of projection of images and tomography. Now, I want to go in first into a bit of mathematics. In the second lecture, I would like to go more into the physics. How would you realize it? So first of all, I have to recap Fourier transform, what that is. And I assume that you are all familiar with Fourier transform itself. The idea is, so I'll go very briefly through Fourier transform. So the idea is that you can regard almost everything being a wave or a collection of waves. And that is not entirely true that you can decompose every image into such series if you have an infinitely fast change. So very fast contrast between an object and its surrounding. You will not be able to do it. But otherwise, it's a very, very, very nice way of decomposing the world. First of all, I want to remind you that you have one organ that can do Fourier transform by itself. That is your ear. When you hear sounds, it seems to us that we are recording something in the temporal domain. I'm uttering one word, and after one word, there comes another one later in time. But when we are hearing sounds, voices, and the height of the voice is perceived by us, that is just its frequency. When you talk about the tone is the collection of frequencies. So it's not only the ground state, but also the higher modes that are present in your ear. So your ear can very, very simply decode frequency information converted from time series. On the other hand, it's very interesting that while you are hearing frequencies, your ear does not Fourier transform the whole time domains from now on until the end of your life, but just a small pace of it. So it's like a time-dependent Fourier transform your ear can do. So for a certain frequency domain, so very high frequencies, it will be transformed by your ear. Very low frequencies, so temporal changes in a very low time domain, is going to be not transformed into frequencies. So if you have an organ to do Fourier transform, you can try to listen with that organ to make, and then maybe automatically you will understand something. So if you want to decompose very simple step function at 0 goes down to -1 and goes up to +1, then the first mode is going to be something like a sine. And then if you put on some higher modes, I did not put on every forthcoming mode, but more modes thereafter, a correct summation will at the end form your step function up and down. I took this example because this is an example when you cannot do the Fourier transform properly. At the edges, you see this peak coming up and this peak going down. And even though you are going to higher and higher frequencies at finer and finer modes, this will be still present here. It is called the Gibbs phenomenon. So basically, what you can do, you can decompose everything into waves, except for very, very sharp jumps up and down. I'm almost sure that you've all known that. What you can also do, that you have these frequency components. Now it's in frequency domain, you can see that certain components correspond to these. So the blue one, the green one, and the red one. What you can do in this frequency domain, you can apply a function that you multiply your original frequency domain function with, and then transform it back. Why is it useful? Because Fourier transform will decompose your function into lower frequency variations and higher frequency variations. So in case you want to increase the higher frequency part of your image without distorting it much, you can just try to multiply the coefficients at the higher frequency domain. Why is it good? Because you can enhance the finer details. If you go to image space, it will mean you will get a sharper image. Or the other way around, when you have a very noisy image, noise makes a very high frequency change in space, because it may just jump up and jump down in an infinitely short time. You can filter out the very high frequency part of this image, meaning you can decrease the noise. You can see the left image. I just took it from the net, and I think it's mine. And this is a quite blurry image on the left-hand side. On the right-hand side, you see it sharper. And the only thing I've done is that I multiplied the high frequency components in the Fourier domain and then transformed it back. So you can use the Fourier transform to sharpen your image and enhance it in that fashion, or you can use it to filter out noise and for many, many, many other things. How would you do this Fourier transform? Let's say you have a signal of a perfect sine, and then you have a trial function, so one of these Fourier modes. You just take the product of the two functions and integrate. And if it comes out to a certain value, let's say 0, then this red component is not important. If you make a trial function that is like this black one, then you will get everywhere a positive value. Its integral will be high. So that's how you can do the Fourier transform, by trying out all the different frequencies and doing the integral. Whoever has learned Fourier transform before can do it in a more mathematical fashion. Some examples. Here, some image, it's 2D Fourier transform. I put this examples here because in time domain, maybe it's easier to imagine that a certain time series can be translated into a composition of different frequencies. But in image domain, you may have to think differently. So you say that in a 2D, for every different line, you have a different function, jump up, jump down, here, somewhere else. How would that look like in frequency domain? You can do these transforms. If you have a dot in the middle, you will get something like that for the two-dimensional Fourier transforms of frequency and frequency on both sides. And the grayscale value is the height of your Fourier transform. If you take more different images, like colored images, first you have to put it into grayscale to make it a scalar function, or you can take the channel separately, and then you get the Fourier transforms. If you have a Fourier transform, you can transform it back and get the original image perfectly. So this transformation preserves all properties of the original function, even though visually you cannot perceive. Like in yesterday's lecture, I've talked about that you can take my photos numbers, like pixel values, and all the information is there, still visually you cannot perceive. That is, you can call it a transformation. Now, this one you can also call a transformation. You get all the numbers, but visually you cannot perceive it as some information you can absorb. Still, all the necessary information is there. And for that image I shown before, this is the Fourier transform. So now I showed you a one-dimensional story last lecture, saying that you need a line of response to connect a certain pixel with one line of reality. Now, if we go to 2 dimensions, we have to transform these images yesterday, saying that you have an object instead of being in one single plane. You have an object in 3D. So a line of response will pass through many parts of the object, many points of the object. So it is not enough to constrain ourselves saying that one point of the object is only reflected on a single point of your sensor, but really we have to work with this line. And if we are talking about nuclear medicine, you have to integrate all the concentration along this line to get all the signal here, because from a certain line of response, you get all the gamma photons, for example, coming through your pinhole. That is going to be the integral along this line. So if we want to go into mathematics, I really want to do it just for a bit, then you have to first work with lines of responses, how to make parameters of them. If you want to say, okay, I'm talking about this particular single line, you can draw it very easily. Visually, you say, okay, I see what you talk about. Mathematically, I have to come up with a parametrization. This is done conventionally, in a sense that you take an omega unit vector pointing to a certain direction. And if you have a line, it will be perpendicular to that line. And the distance from the origin to that line will be the number t. So if you have omega and you want to arrive to this line, and someone tells you, okay, here is your omega, here is your t, then you just have to draw an omega that you've got, so you know the direction, have to walk t distance until this line, until the end of the vector, and then perpendicularly you will get the line we are talking about. This omega has just a theta and a parameter in it, so the cosine of a theta and the sine of a theta. Theta is measured from the x-axis. So you need basically 2 parameters in a 2-dimensional plane. One is theta and the other one is t. So if you give me these 2 parameters, theta and t, I will just measure this theta on the axis x. draw a unit vector. Then in that direction, I will walk the distance of t, and I will arrive to this line. If I do that, I will have a parametric representation of a line. If I have that, I can do whatever functions integral on that domain. And I would do that because in nuclear medicine, as I explained, you would integrate along that line all the radioactive isotope concentration. If you talk about X-rays, it will still take another step further. You have to take the normalized logarithm of the incoming intensity at your X-ray detector, but still you would arrive at an integral of the attenuation coefficient of your object. So basically, we are talking about the same idea here, integrals along the line. Let's see what I'm talking about. This is an image of a fall, and you take that line. You will get in the grayscale domain some intensity profiles. Now this white is here, this white is somewhere there, and in both X-ray imaging and nuclear medicine, gamma cameras and positron emission tomography, you do the same. You actually get, by the measurement, you are actually measuring this line integral of, in one hand, the concentration of the isotope, on the other hand, the attenuation coefficient. Of course, not perfectly, but this mathematical model is quite good to describe this phenomenon. So if you have such a function along this line, and if you integrate it, you will get the so-called radon transform. This will be the function in question, let's say isotope diagnostics and the concentration of the isotopes. You do the line integral, and this line will be characterized by the two parameters I explained before. If you put that in mathematical terms, then you will get the radon transform with parameters t and theta that will tell you which line we are talking about, and this is going to be the integral. First of all, in a direct function formalism, to say, okay, if t equals to omega times x, that's the time when we are talking about this line, and then those values needs to be only taken for the integral, so you'll get a double integral, or you can make a parametric representation to say, okay, I will go a distance of omega times t here. I will turn my head to the perpendicular direction, omega perpendicular, and then I will go a distance of s in both directions and do this integral. If you put out it in 2D in the formalism I used with cosines and the sines of t, basically this integral has to be evaluated. It's not easy. You cannot do it analytically for many functions, but you can do it for a circle. Quite simply, you can work out the math that's here, or you can say, okay, if I want to do a line integral of this circle, the only thing that matters how far I am from the origin, because this distance from here to there will be the integral domain. And if this circle has only a single value here, let's say 1, and outside of this circle you get 0, you basically just have to calculate this length, and that is this number here, this expression here. We have to take it 2 times from one side from the red arrow and the other side. So you get that one, or you can do the formal integral as you wish. So that's how radon transform works. If you take a single point-like object and you do the radon transformation, I want to jump back. You can see along which parameters, which lines you get some reasonable values. For many lines on this plane, if black is 0 and white is 1, you will get a line integral of 0 because it goes through the black, so you integral 0, so you get 0. But only for some lines you get non-zero values, and if it's exactly a small dot, you will get something like that. It's here. It's something like a sine wave. This is theta and t. Those are the parametrizations of your lines along which you integrate. And you see that for certain T's and thetas, you get values. That's the blue, that is not 0, and all the white here is 0 now. If instead of a dot, you get a circle, you will get a broader sign here. Why is it a sign? It takes a bit more mathematics, but because it looks like a sign for a single point in a real image space, then this T theta radon transform space, it looks like a sign. We call this representation a sinogram. So it is also a transform like the Fourier transform. I am telling you that you preserve all the information. You can recreate the original object from this data, and the same as Fourier transform, because you cannot see from the sinogram image what was the original. If you looked at those sinograms a lot, you will see that, okay, every sign function corresponds to a dot. So you can get used to sort of getting an understanding what sort of objects you may have, many point-like objects or not. But otherwise, from this image, you don't see the original image, but all the information is preserved. Some other examples. Radon transform of a square in sinogram space. Here you have theta, here you have t. You will get now not only blacks and whites, so not only zeros and ones, but also other grayscale values. Down here, you can get the so-called Shepp-Logan phantom that is constructed from ellipses, and it should represent, or supposed to represent, the brain. And it is done, and you always get it when you do medical imaging, whatever publication, that you have to publish what your Shepp-Logan phantom transformation and back transformation would look like. Because based on the circle transform, the radon transform of the circle I showed you before, and applying some theorems, you can actually analytically create the radon transform of such an object. So far, it is a circle slanted or scaled along to whichever axis, and maybe shifted away. You can handle this analytically. Okay, so how would you do the transformation back? Now I would ask the organizers whether I could just, without stop, proceed to my second lecture, and then I can connect the two parts. I'm not hearing any answer. I'm taking it as a yes.
Ah, okay, yeah. Sorry. after a year of COVID, it's still you forgot to unmute. No. So yeah, please go ahead. So you share your screen anyway, yeah?
Yeah. Okay, I will go through and then switch to the other presentation, but then I can make this one longer a bit so I can get to the end of the story.
Okay, but excuse me, you plan to finish by 10 o'clock or?
Yeah. That's the idea.
Okay, perfect. Whatever you. Best.
Yeah. I'm sorry I was late, but I don't want to push my take further. So. Okay, so if I take this image of the fall, again, put into grayscale, and do the radon transform, that would be something that you could get out of a CT scanner, or you would get that out of a positron emission tomography machine or a gamma camera. You will get these measured data. These are, again, angles, and these are the T offset parameters. So this would be your measured data coming out of the scanner. But I now did it analytically using MATLAB. In MATLAB, you can, if you want to experiment with it, there is the radon command and the iRadon command. iRadon is for the inverse. So this is what you will get out of the scanner, and you will have to find the transformation back to this image. And the idea is, again, the same for the CT. You spin your X-ray machine around the patient. For single photon emission computed tomography, you spin your gamma camera around your patient. And for positron emission tomography, you sort some coincidence counts. I will talk about these a bit later. Okay, when this Johann Radon, a Czech mathematician, invented the inversion formula in 1917, it looked like that. It took really a mathematician to come up with this formula, and you cannot apply that for machine-based data. The problem is that if you want to do these integrals, you will always make the denominator 0. So you will go through always the pole of 1/0. So this integral only exists in a principal value or Cauchy principal value sense. So you can't really do that with computers, but for the computed tomography, you have to wait for the computers to arrive because you can only do basically this inversion numerically. This jumps off. Okay, so there is this theorem saying that if you do a Fourier transform of the sinogram, but only along the t direction, so let's say along this red arrow, then you will arrive to the two-dimensional Fourier transform of your image. And then you can actually convert back into the real image, as we have, as I tried to show you before, at least revise this information for you. Hope you believe if you haven't ever heard about Fourier transforms. And if you do that in sinogram space, you will get here all these still the theta values, and here you will get all the frequency values now. So instead of this sinogram, you will get this something like the skin of a zebra. And if you do that, you get the two-dimensional Fourier transform of the image that will be not very well sampled. I'll skip this part. But if you do some math, you will arrive to a formula that looks like this one, looks like a mumbo jumbo, but I will explain. Here is your Radon transform. This symbol goes for the Fourier transform. And if you have Fourier transform your image, but only in the sinogram space, only along the p direction, you will get a frequency variable r in my notation. You have to multiply it with this r absolute value that comes from a Jacobian from the mathematical derivation, and then you have to Fourier transform it back. So you take a function, Fourier transform it, multiply with another function, transform it back. That is nothing else but a filtering process that I explained earlier, that you can make an image sharper or blurrier or whatever. So you can change its appearance, change the weight of the frequency component at your leisure. Now mathematics says you have to do it with this filtering function, r absolute value. If you do that, I'll not go through the math, you will get a filtered image. Now there's a second part. You will, if you do that, you start from sinogram space, go through Fourier space, go back from Fourier space, you are still in sinogram space, you are still not getting an image. So what you have to do is another part that is important, that transform you back from the sinogram space into the image space. How would you do that if you only have intuition and not much mathematics? But you know that every point of the sinogram, for every theta and every t, you get a value that is corresponds to an integral of a line along this image. For every t and theta, very easily you can find this line and say, okay, this white dot came from, for example, integral along that line. So it must go through very light points, right? So what if I will go back in a fashion that I will take one point of this image and check all the corresponding lines going through that point and take the average of them. It wouldn't be a bad guess, right? So I will just take this point, for example. I'll check, okay, this line goes through this point. Where is that? It is with this t and theta. Okay, that's so it's a high value. Okay, I have a high value. Let's take another line going through that point. Okay, this one's a low value. Let's make an average. And maybe that is correspondent to the information related to this point, because all the other lines do not go through this point. So they should not bear any information on this dot. I hope you got this one. It's better to give this one in online offline lecture, because then you can get some feedback. But okay, if you understand this process, you can go through every point. And for every point, you check every line going through that point. And for every line, you check in your sinogram space or your data space coming out of the scanner, all the values measured, and then average them, and then put it in that certain spot. If you do that, you will get such an image. It's called the back projection. You can sort of see that you see here the horse. The shape of the horse you can sort of see. So now let's combine the two processes and go along the mathematics. And say, this formula says, first you have to filter your sinogram with this Fourier transformation, and then you can do the back projection step. So let's take only a single line that is at 200. Let's take the function value of your sinogram. It will look like that. This is at the 200th angular step. Let's take the Fourier transform. You'll get it here. Let's multiply it by the R absolute value. You will get that one. And let's transform it back. You will get something like this image. So we started from that one, like heels up, down, heels up, down, heels up, down. And you arrive to still the same heels, but now all the values go down to 0, and the peaks are a lot sharper. So this filtering took off the low frequency parts and intensified the high frequency parts of this function. And I would do that for every single line separately on this sinogram in my data space. So with the data coming from the scanner. Okay, so you see that that was the original image, and that transformed to this image. We can sort of compare it for a second. If I do that for every single line, I will get to go into Fourier space. I'll get this one. So here angles, and here are the frequencies. And I will do the filtering, and I'll transform it back. I will again arrive to a sinogram. Original sinogram, new sinogram. Original data, new data set. You see it's a lot sharper. It's a lot sharper. It's a very soft image, and we don't know what's on it, but it's very sharp. That's for sure. And now you can do the back projection step. Now you can sort of fish out for every point in the image space the lines and the data corresponding to that dot. Okay, if you do that, you will get this transformation back. And you see that you really got all the details, even the hairs on the chin of your fallback. So radon transform and its inverse is capable of preserving all the information. And we have a computing technique that goes from radon space back to normal. And as we can very well model our data coming out of our CT scanner and nuclear medicine, whatever image, gamma camera SPECT, and the positron emission tomography, we can, from the measured data, get back to the real image space. Okay, and now I want to give you a hint, if you haven't done your homework, how to solve this homework. That was one idea I showed you, saying that, okay, with difficult mathematics, you can arrive to inverting your measured data into some image space object. But there could be other techniques that maybe could be more familiar to you. Let's take a step back and say we have this image, and along these lines we have the integral of the values we are talking about. It's easier to formulate everything in nuclear medicine terms, because then you will get just concentrations in this green area, and you have to take the image of this concentration distribution. So let's say you have a line going through your object. You will get small, you can make small parts of it. They are called voxels, so-called volumetric pixels. So in short, voxels. You can make whatever partition, but the easiest is to have a Cartesian one. So you have these small voxels, and in every voxel, you imagine the concentration to be homogeneous. So you get the same concentration at voxel, and if you want to make a finer resolution, you make more voxels out. That's simply like that. If you take its integral, you actually just have to walk through this grid and then integrate all these small lines and multiply with the concentration at a certain position. Now, in reality, this would be gamma photons coming out of, for example, gamma photons coming out of your patient. They can scatter, they can get absorbed, and so on and so on. So from every voxel, there is a probability to contribute to a certain line of response. Now you have two detectors at the end of the line of response because it signifies more a positron emission tomography setup, or you can imagine it like that. So if you measure along the line some hits, they must have come from the voxels here, and that would be the X concentration multiplied with the probability that they would contribute to this line of response. Because a gamma photon may go that direction, that direction, that direction. It needs a certain probability to go in the right direction. Plus, it needs to have some time arriving to the to your detector. It needs some probability, luck, to get to the detector. So if you multiply the chance of your concentration, the chance of hitting the detector with the concentration, you will get your measured data. So Y is your measured data, X is your concentration you are interested in, and A will be the probability of getting from here to there. Now there should be a vector with all the possible voxels in it. Y should be a vector with all the measured data separately, and A would be a matrix connecting the two. But what you can see, it's a linear connection. And if it's a linear connection, then you have a chance to get this inversion. So what can we know about this matrix is that it is a huge matrix. Normally in a PET scanner, X is in the range of millions, Y is in the range of 10 millions. If you multiply the two dimensions, you will get to the size of A. So it's a huge, huge, huge matrix. On the other hand, lines not going through certain voxels will have an almost zero contribution to your detector. That means this matrix will be huge, but most of its elements will be zero. That's called a sparse matrix. It's very hard to work with it, but if you find a way to work with it, then you get perhaps forward. Now, there is a strategy to go one step ahead, and that is to apply a maximum likelihood strategy. If you have measured these Y values, that is a number of hits in a certain line of response, then maximum likelihood strategy will ask you, what is the most likely distribution of the concentrations in the voxels that could cause the measurement? Again, so let's say if I put whatever radiopharmacon concentration in the voxels, whatever, there is a chance you will get a certain measurement out of it in your PET scanners. And whatever measurement you can imagine. But it's very, very unlikely that you will get all these. You can just arbitrarily pick a certain concentration set and a certain measurement set and say, okay, this concentration set caused that measurement set. But it is possible. Now we are saying that, okay, but we are looking for something sensible, right? We're looking for something provable. So now the idea is to say, okay, what is the most probable concentration distribution that could have caused the certain measurement outcome to happen. And this is the maximum likelihood strategy. I'm also hoping that you are familiar with this concept, or at least heard about it. So I'm repeating for the third time. Now, you want to maximize the probability that a certain measurement has happened by changing the concentrations to a distribution that is the most likely that has caused your measurement. It's a very twisted, very nice thought, but and usually gives the most accurate answers, but usually it's very hard to find this maximum probability. One technique that they commonly use in nuclear medicine is the expectation maximization iteration method, because directly you could not do this maximization yourself. And what is the idea? Here you have the formula, and in the other presentation I have spelled it out a bit more understandably. But the idea is, for this measurement, is the following. Let's imagine we have a certain set of concentrations in your voxel space, and you have all your measurements. Your measurement is for sure, you already measured, you can't do much about them. And in my homework exercise, and you can work out at home, you got the data. Now, if you suppose whatever concentration here, concentration distribution, let's say 1 everywhere, the idea is that you calculate using this system matrix A for this concentration set, what measurement value would I get? If I assumed everywhere a 1, that was not the reality for sure, then you will get the sum of all the concentrations and the probabilities along this line for this line of response. And when you have calculated that, you will see whether it was an overestimation or an underestimation. You divide the values with each other, and with this division will tell you if I overestimated a certain line of response, that means all the voxels participating are an overestimate, so I have to decrease them. And if it's a lower value, then you say, okay, I might have overestimated, so I have to decrease them. If you do that for every single line, and afterwards you take a single voxel and you tell, okay, corresponding to me small voxel, I see all the lots, not everyone, but a lot of them. And I have this ratio all around saying whether the original guess was an overestimate or an underestimate. You can just take an average of them and say, okay, what is the average overestimation regarding this voxel? And then you can do a multiple of with that, and the original concentration that you have guessed. And that will bring you one step closer to the final solution. Okay, and maybe it was, I'm guessing it was too fast. So whoever reads MATLAB, I will send a small MATLAB code that will do the inversion of your homework. And if you read MATLAB well enough, or just at least some, you will see how this iteration scheme works. Now I'll switch over to the representation that I finally have not lost. Okay, and I'll go through it very, very briefly. I have a very short time left. So I wanted to show in this lecture are the machines in nuclear medicine. So I'll go through that once very fast, and I'll leave those that I wanted to talk more about, in detail in here. Okay, I already showed you last lecture. It was supposed to be only a recap. That you have position emission tomography and gamma cameras that you can use for tomographic imaging. So what else would we need to realize all the measurements along different lines? We already talked about its position sensitive sensor, something that makes a line of response, a pinhole, a collimator, or the coincidence detection in position emission tomography. You need a source, radiopharmacon, for example. I'm doing now it more for nuclear medicine. As for X-rays, you have seen the laboratory as well. You need photons exiting the patient. You need, of course, quality assurance and radiation protections. And you also need a very nice question to answer. And that would be here functional information. For nuclear medicine, you would need, according to the tracer principle, some compound that you can bind your radiopharmaceutical to your radioactive isotope to. And this will show you some information how your body functions. So instead of where is my liver, that is the question, but how does my liver function? Does it take up the radiopharmacon too fast or too small, or does it not take it up homogeneously? So there is like one part that is not functioning anymore, and so on and so on. So let's go through the most important part. This is the position sensitive sensor that is not easy to create for gamma photons. I will now go through some parts I will have not time for. And that was in 57 when Hal Anger created his camera. And his idea was not to detect the gamma photons position sensitively in a fashion that is affordable and gives a nice enough resolution. What is the main problem? Normally, you would have a scintillation detector to absorb the gamma photons. So you need a bigger crystal because gamma photons can penetrate through larger bits of material. When gamma photons light got converted into visible light, your photomultipliers will intensify this signal to get a measurable, detectable electron signal. So far, I think you are familiar with this technique. You have heard it, or you will hear about them quite soon. It's good. You can make one big crystal, and then it will count all the photons rising. Moreover, it will count all its energies. Very, very good. So now you would need a big collection of them. Problem is that very hard to make the photomultiplier small, very hard to make the crystals too small, and gamma photons will not get absorbed into a single crystal. So it would be very expensive. So the idea was that Hal Anger came up with is to say, what if I would have all traditional images, many scintillators, but these scintillators will be used in a fashion that more photomultipliers would see a certain crystal. And I'm trying to get this image I was looking for. Okay, so let's say you have here a scintillation detector crystal, one big crystal, and you will put more scintillation photomultipliers behind it. The gamma irradiation would come from this direction and will make a collision in the sodium iodide crystal. The visible light will go to this glass window and this light guide, and it will spread. It will spread to photomultiplier B, photomultiplier A, and photomultiplier C. If you get this gamma incident at x equals 0, you will get most of the visible light going through into photomultiplier B, and less will go to photomultiplier A or photomultiplier C. So with this weighted average, with the position A, B, and C, with the signals coming to this photomultiplier, this one and that one, you can guess an incoming energy position. So now it says here, you will have the A, B, and C photomultipliers. And if you have now here, at this point, your incident gamma photon, your photomultiplier A will get most of the visible light, so highest peak. B, I think it's mixed up. B will get less, and C will get the smallest. And with the weighted average, you will get the position out of it. Now, make it two-dimensional. So let's put it in top view. And from top view, you will get an incident gamma photon here in a huge scintillation crystal all around. The gamma photons energy will be converted into visible light, and this visible light will go into photomultipliers here, the 1, 6, 5, and 4, so all these. And with the weighted average, you will guess, okay, somewhere here, the detection must have happened. If you take such a reading, you will get these raw data out of it. Okay, I was going to talk about collimators a bit more, but I will not have time for it.
David, there's a question from Tobias. Are the PMT working in pulse or DC mode?
Well, for the photomultipliers, I'm not really sure about the question. I would translate that. For every incoming photons, you will measure the full signal, so the signal strength. So it's not only the count that you measure, but you also have to get the energy distribution. And with that, you can filter out those photons that have scattered in the body, so you have lower energy than the original one. So you can get rid of scattering events. I'm not sure if I answered the question correctly.
Tobias, you want to unmute yourself and respond?
Yes. Can you hear me?
Yeah.
Yes. No. Thank you. That was actually my question. If you are actually detecting single pulses, or if you are detecting a constant signal, like in the case of photomultiplier or even silicon detectors, would be a DC current. But yes, that answers my question.
Actually, you will get in that. Okay, if that such is the question. Okay, then you will get the current and measure the full signal strength. So you will get the energy distribution as well. It's quite important. If you would not need the energy distribution, you will not work with scintillators, perhaps definitely not with photomultipliers. In CT scanners, you don't need the energy distribution. So you will get some simple detectors there, so like very small gas chambers, but now most likely some silicon detectors. So very simple, like normal photo cameras even, that detect the scintillation light. So if you don't need the energy, you don't need the photomultipliers. For a positron emission tomography and for a single photon computed emission tomography, you definitely need. For positron emission tomography, you have to filter out the 511 keV photons and only the coincidence of them to make sure that photons came from the same line of response. And for gamma cameras, the original energy of the isotope should be filtered out. So all the scattered radiation is eliminated.
Okay, thank you.
Okay, I think I've run out of time. I still wanted to talk about many other things, but not finding the proper presentation, it took me longer time to explain the previous one. I hope you still benefited from it. I wanted to show how these images look like in reality, and also some artificial intelligence techniques, how to enhance image properties. Okay, I will send you the MATLAB file for anyone who is interested, and I will also tell the organizers to which questions I didn't have time to tell the answers to, if it's not obvious, because the list of questions I sent will not be complete with this presentation not walked through properly. Okay, so that was from my part, and I will give the option to Mate to proceed.
Okay, thank you very much, and thank you for keeping with the time. It's always so. I don't. Are there any further questions? We still have 5 minutes for some more questions.
A question is, where can we find the MATLAB code? Well, I don't know how you would be able to distribute it, but I'm sure there is a channel. Question.
Well, there is, yes, there's the Google file. So I think Sila, I think you're distributing information to the group, are you? Sila? Actually, Sila should run the next video anyway. So while Sila is not there, I think you can continue.
Yeah, well, I would love if I get the chance. I can still talk about other things. So I already shared the presentation, and I hope Gila will say something when I have to stop, if that's what you meant.
Yeah.
Okay, what is quite an important part is how to get the isotopes produced when you want to get radiopharmacons. And if you look at the stability map of the elements, you will have the number of protons here, number of neutrons here, and the binding energy. You will get around iron something low, and then if you go above, you can fusion. If you go up, you can fission isotopes. But for us, what is more important, more these lines. If we have something, and how you to get spontaneous migration in this line, you will get two types of isotopes now. What is one is for single gamma emitting isotope. So you want to get a gamma emitting isotope, and for that you would need a surplus of neutrons in the nucleus. If you have a surplus of nucleus, it wants to if you need surplus of neutrons. If you have a surplus of neutrons in the nucleus, then it will try to somehow disintegrate into a proton and a beta radiation, so an electron. And after a beta radiation, you usually get gammas out of it because your nucleus is in an excited state. So if you want to produce gamma emitting isotopes, you would like to feed your isotopes with neutrons. You can make fusion sources like deuterium shot into tritium or deuterium into deuterium, but most likely you will get a nuclear reactor. If you want to have a positron emitting isotope produced somehow, you would like to feed your nucleus with protons. If you have a surplus of protons in the nucleus, then somehow the nucleus will try to eliminate these protons and convert them into neutrons. They can capture from the inner shell some electrons. So with this captured electron, the proton can transform into a neutron, or it will just borrow from the universe some electrons and create a positron as electrons antiparticle in return. So if you want to do that, you have to get protons shot into an isotope. For that, you can get hydrogens, take off the electrons, accelerate these protons, and then shoot into the nucleus. How would you do that? You can do it mostly with cyclotrons. You could do it with LINEX as well, but cyclotrons are more compact. So you do that. For whatever reason, usually they do not take off the electron and accelerate, but add a surplus electron to hydrogen. So it will have a negatively charged electron, negatively charged hydrogen accelerated, and it will be shot into the object through some filter, like a carbon layer that takes off the electrons. And that's how you will get your isotopes. The most well-known isotope for a single gamma photon emitting isotope is technetium, when you have molybdenum fed with neutrons, and that decays into technetium metastable state spontaneously. And these are different elements. So molybdenum is not soluble in water. The technetium pertechnetate isotope is. So it is possible just to get water through the molybdenum to wash out the technetium. And then this technetium will be injected into the patient. And for that, you will get a 140 kV radiation out. If you go to positron emission tomography, you will get the cyclotron, and with the cyclotron, you will have electric field accelerating these protons, put it into a magnetic field pointing now upwards, and it will force these protons to go in circles around and around and around, while in a larger and larger radius circles. At the end, it will leave the cyclotron. What they usually use is the fluor made out of a reaction of taking oxygen 18, and in the proton-neutron reaction, it will become fluorine 18. And this fluorine is put into sugar. The way it's done is you take a sugar, it's a glucose, and you take off one oxygen. So this will be a desoxyglucose. And you replace this taken away oxygen with fluorine. So you will get fluorine desoxyglucose. So this one it is. So you get a sugar molecule, and this oxygen will be taken off, and you put here fluorine. Why sugar? Because the sugar intake of tumor tissues are very high. So you would take all the sugar together with the positron emitting isotope. And that means that you will get a positron emission image of all the cancer tissues. Do I still have time? Shall I go on?
Well, oops. I think if you need 5 more minutes, we could still run your presentation for 5 more minutes. Then we're running 15 minutes late in total, and then we could.
Yes, I think I answered again some questions in the piece. So.
Yeah. And David, if you would like to share something, send me, and I will put in a drive, and I'm going to share for the student.
Okay, then I will do that. I think I will then finish the presentation now. Thank you for the attention. I will send this MATLAB file for anyone who is interested and want to work out how to solve the puzzle I gave you. So that's it from my part then.
Okay, thank you very much. Yes, Sila, there was the question whether how we share information, but you share the information through the Google Drive, and that's what I understood. Yes, you're muted. Sila, you're still muted.
Sorry, sometimes happen. Okay, I make a Google Drive. I will send to David the link, and he will put what he wants, and after that I can share it for the student. Is it okay in this way?
Okay. Yeah. Okay.
Good.
Thank you very much. Thanks a lot, David, for being flexible and jumping in and out. And yeah, so Sila, I think now you're sharing a video, and the questions, can they come to you, or how do we arrange the questions for the next?
Yes, if I can, I will answer. Maybe
Okay.
I can know everything because their specialties is different as mine. But if I can, I will answer. Yeah.
Okay, so I'll let you share the presentation.
Can you see it?
Yes.
Good.
Dear ladies and gentlemen, my name is Máté Lajos, I'm a physicist, and I would like to present you some aspects of radiation protection, such as sources, dose definitions, nuclear detectors, and so on. What do you think? How do radioactive materials, radioactive sources look like? Answer is tricky, anyhow. In lucky and regular situation, radioactive sources have the signal of radioactive hazard on their package, on their holding, or on their storage device. Radioactive materials can be solid, liquid, and gas. They can be sealed sources when the radioactive material cannot interact with the environment. Radioactive material cannot be discharged to the environment because of the special coverage of the radioactive material. Of course, the radiation of them is measurable. We call them unsealed sources when the radioactive material can be interact with the user, with the environment. For example, liquid radioactive sources used as tracer. We distinguish three main ways of radiation decays: alpha, beta, and gamma decay, or alpha, beta, and gamma radiation. They arising from nucleus. Alpha particle is a helium nucleus, beta particle is an electron, a positron, and gamma particle is a photon. Atoms with the same atomic number but different neutron numbers, and hence different mass numbers, are known as isotopes. During alpha decay, the atomic number reduces by 2, the mass number reduces by 4. During beta decay, the atomic number increases by 1 in case of negative beta decay, or decreases by 1 in case of positron decay. The mass number does not change. During the gamma decay, atomic number and mass number do not change. Nucleus emits a gamma photon. Alpha particle has positive electric charge. Electron has negative. Positron has positive charge. Gamma photons have no electric charge. Charged and heavy particles can be attenuated effectively. Alpha particles can be stopped by a piece of paper. Beta particles can be stopped by a plastic layer. Gammas are stopped by a thick lead layer effectively. Alpha, beta, gamma, and neutron radiation interact with matter by different ways. Charged particles interact strongly and ionize directly. During the interaction, X-ray and gamma photons are produced. Neutral particles, such as photons and neutrons, interact less, ionize indirectly, and penetrate further. Penetration ranges in tissues depend on the type of the radiation, the energy of the particle, and the type of the tissue, effective atomic number of tissue. Even high-energy alpha particles cannot penetrate the skin surface. Beta particles penetrate some millimeter in tissues. Gamma photons penetrate easily, even more than 1 meter, since we can measure the radiation of a patient after being injected gamma-emitter radionuclide. Interaction of gamma photons with matter has three main forms. One-off photoelectric effect. The photons have a characteristic energy called photon energy, which is proportional to the frequency of the light. In the photoemission process, when an electron within some material absorbs the energy of the photon and acquires more energy than its binding energy, it is likely to be ejected. If the photon energy is too low, the electron is unable to escape the material. During Compton scattering, the incoming photon collides with the free electron and transfers its energy partly. Results of the process are scattered photon and scattered electron. Pair production. The incoming energy of the photon must be above a threshold of at least the total rest mass energy of the two particles created. Then this process spontaneously can produce an electron-positron pair. The Curie reaction depends on the photon energy and the atomic number of the absorber. In lower gamma energies, photoelectric absorption is the dominant reaction. In middle gamma energies, the rate of Compton effect will increasing. Above 1022 keV pair production will be dominant. Positron annihilation happens after pair production. Positron collides with an electron and they transform to energy. Two gamma photons are produced with energy 511 keV. Breaking radiation. Wilhelm Conrad Röntgen discovered it on 1895. He named it X radiation to signify an unknown type of radiation. When a charged particle, mainly electron, lost its energy in the electromagnetic field of the nucleus, X-ray is produced. X-ray tube is a vacuum tube. As with any vacuum tube, there is a cathode which emits electrons into the vacuum and an anode to collect electrons, thus establishing a flow of electric current, known as the beam, through the tube. A high voltage power source, for example 30 to 150 kilovolts, called the tube voltage, is connected across cathode and anode to accelerate the electrons. The X-ray spectrum depends on the anode material and the accelerating voltage. Electrons from the cathode collide with the anode material, usually tungsten, molybdenum, or copper, and accelerate other electrons, ions within the anode materials. About 1%, only 1% of the energy generated is emitted, radiated as X-rays. The rest of the energy is released as heat. The range of photonic energies emitted by the system can be adjusted by changing the applied voltage and installing aluminum filters of varying thicknesses. Aluminum filters are installed in the path of the X-ray beam to remove soft, non-penetrating radiation. The number of emitted X-ray photons of those are adjusted by controlling the current flow and exposure time. Ionization is one of the principal ways to radiation, such as charged particles and X-rays transfers its energy to matter. During ionization, electrically neutral atoms or molecules are converted to electrically charged atoms or molecules, ions. Some dose definition. First, absorbed dose. Absorbed dose is a physical dose quantity representing the mean energy imparted to matter per unit mass by ionizing radiation. Dose rate is absorbed dose per unit time. Equivalent dose is a dose quantity representing the stochastic health effect of low levels of ionizing radiation on the human body. Only on the human body it is important. It arises from the absorbed dose multiplied by the radiation weighting factor. Effective dose. Tissue-weighted sum of the equivalent doses in all specified tissues and organs of the human body. It represents the stochastic health risk to the whole body. However, we use several other operational dose quantities. For example, ambient dose equivalent, H-Starten for the measurement of workplaces and use it for control the effective dose. Other one is personal dose equivalent, which is used for individual monitoring. It is well known that natural ionizing radiation is part of our life. Cosmic ray is a component of our natural origin exposure. Natural background radiation is variable depending on the geological environment and the altitude. Think of your last flight when you were traveling 5 microsievert per hour. Ionizing radiation has adverse biological effects. How to protect against ionizing radiation? The protection from external ionizing radiation has 3 main forms. They are time protection, distance protection, and application of shielding materials. The less time you spend near the source, the less dose you receive. The greater distance you keep from the source, the less dose you receive. And using appropriate shielding material, you will be less exposed. Using appropriate material for shielding is important. The used shielding material depends on the type and energy of the radiation. For example, lead shielding materials with high atomic number shields gamma and X-ray effectively. Beta particles can be stopped by a layer of plastic, alpha particles can be stopped by a sheet of paper, or even by your skin. There are some main differences between radioactive material and X-ray machine. X-ray machine needs electricity. Radioactive materials don't. Radioactive materials run out in a given time. They have to be deposited as radioactive waste after usage. X-ray can be shut down. Radiation is over. However, radioactive material cannot be shut down, only can be shielded. How can we protect ourselves? In dentistry, the personal protection for patients is provided by lead apron, 0.25 mm lead equivalent. Using CR mobile X-ray devices, the protection of the user team is crucial. Distance protection is limited applicable, so personal protective tools are required. Not only personal protective tools, but instant shielding is also required. Hanged transparent lead shielding above and hanged lead curtain middle and down 1 mm lead equivalent. Front and back protection have to be considered. During X-ray monitored surgery, eye and thyroid protection is also necessary. How to detect ionizing radiation? That's an emphasized question. Radiation has no color. It is invisible, has no voice. There is no heat effect or burning effect immediately, so you only can detect that with appropriate nuclear detectors. As mentioned previously, absolute dose is a physical dose quantity representing the mean energy imparted to the matter per unit mass by ionizing radiation. The mean energy imparted to the matter could be measured via its heat effect, but the high specific heat capacity causes low temperature change. It is difficult to measure. We use ionization effect to determine the doses. An ionization chamber measures the charge from the number of ion pairs created within a gas caused by incident reaction. It consists of a gas-filled chamber with 2 electrodes known as anode and cathode. The electrodes may be in the form of parallel plates or cylinder arrangement with a coaxially located internal anode wire. voltage potential is applied between the electrodes to create an electric field in the field gas. When gas between the electrodes is ionized by incident ionizing radiation, ion pairs are created, and the resultant positive ions and dissociated electrons move to the electrodes of the opposite polarity under the influence of the electric field. This generates an ionization current, which is measured by an electrometer circuit. The electrometer must be capable of measuring the very small output current, which is in the region of femtoamperes to picoamperes, depending on the chamber design, radiation dose, and applied voltage. Each ion pair created deposits or removes a small electric charge to or from an electrode, such that the accumulated charge is proportional to the number of ion pairs created and hence the radiation dose. This continued generation of charge produces an ionization current, which is a measure of the total ionizing dose entering the chamber. A proportional counter uses a combination of the mechanism of a Geiger-Müller tube and an ionization chamber, and operates in an intermediate voltage region between these. The proportional counter is a type of gaseous ionization detector device used to measure particles of ionizing radiation. The key feature is its ability to measure the energy of incident radiation by producing the detector output pulse that is proportional to the radiation energy absorbed by the detector due to an ionizing event, hence the detector's name. It is widely used where energy levels of incident radiation must be known, such as in the discrimination between alpha and beta particles. In Geiger-Müller tubes, the strong electric field created by the voltage across the tube's electrodes accelerates the positive ions towards the cathode and the electrons towards the anode. Close to the anode, in the avalanche region, where the electric field strength rises inversely proportional to radial distance as the anode is approached, free electrons gain sufficient energy to ionize additional gas molecules by collision and create a large number of electron avalanches. These spread along the anode and effectively throughout the avalanche region. This is the gas multiplication effect, which gives the tube its key characteristic of being able to produce a significant output pulse from a single original ionizing event. The ionization chamber is the simplest of all gas field radiation detectors and is widely used for the detection and measurement of certain types of ionizing radiation, X-rays, gamma rays, and beta particles. Ion chambers have a good uniform response to radiation over a wide range of energies and are the preferred means of measuring high levels of gamma radiation. They are widely used in the nuclear power industry, research labs, radiography, nuclear medicine, and environmental monitoring. Surface contamination measuring device measures the alpha, beta, or gamma contamination on surfaces. Measured value is CPS, count per second, or CPM, count per minute, or becquerel per square meter, square centimeter for a given radiant light. Surface contamination measuring devices can have several coverages, filters, depending on what to measure. For example, alpha blocker or H*10 filter to measure ambient equivalent dose rate. This type of surface contamination measuring device can distinguish between alpha and beta gamma radiation. Alpha particles are catched by zinc sulfate scintillation crystal, betas and gammas are measured by plastic crystal. Measured quantities are CPS, CPM, and becquerel per square meter for the radionuclides in its nuclide library. Pay attention not to contaminate the instrument. With contaminated instrument, you always have relative high signals, but false signals. So you cannot determine the contamination of the investigated surface. Use a thinner plastic coverage to prevent the contamination of the sensitive surface of the device. Of course, you reduce the sensitivity of the detector, but if you only have to determine whether the surface is contaminated or not, it is an acceptable solution. When the sensitive surface is injured, the visible light causes false signal in the detector since with scintillation point. The solution is to increase caution during the usage of this device without its protecting coverage. Remove the coverage only if it is absolutely necessary. Scintillation is a flash of light produced in a transparent material, crystal, by the passage of a particle. A scintillator crystal exhibits scintillation when excited by ionizing radiation. A scintillation detector or scintillation counter is obtained when a scintillator is coupled to an electric light sensor, such as a photomultiplier tube. PMTs absorb the light emitted by the scintillator and re-emit it in the form of electrons via the photoelectric effect. The subsequent multiplication of those electrons, sometimes called photoelectrons, results in an electric pulse which can then be analyzed and yield meaningful information about the particle that originally struck the scintillator. A scintillator crystal exhibits scintillation when excited by ionizing radiation. Cathode of PMT absorbs the light emitted by the scintillator and re-emits it in the form of electrons by the photoelectric effect. The subsequent multiplication of photoelectrons results in an electrical pulse which can be then analyzed. Scintillation detectors are able to identify radionuclides via their gamma energy. They have an integrated gamma spectra analyzer software and nuclide table for identification. They are user-friendly, usually use color-coded identification for artificial, medical, naturally occurring, nuclear, and industrial sources. This instrument identified cobalt-60 isotope via its 1.1 and 1.3 megaelectron-volt emitted photons. During the measurement of a phone smoke detector containing krypton-85, the detector identified fluorine-18 because the annihilation photon energy is very close to the gamma energy of krypton-85. Proportional countertubes filled with boron trifluoride gas are typically used for neutron dose rate measurements. Outside of the countertube, there is a moderator which decelerates the neutrons, making them able to be detected according to the nuclear reaction. Boron-10 isotope interacts with neutron, producing charged particles which can be then detected using the same proportional countertubes. A semiconductor detector uses a semiconductor, usually silicon or germanium, to measure the effect of incident charged particles or photons. In semiconductor detectors, ionizing radiation is measured by the number of charge carriers set free in the detector material, which is arranged between two electrodes by the radiation. Ionizing radiation produces free electrons and holes. The number of electron-hole pairs is proportional to the energy of the radiation to the semiconductor. As a result, a number of electrons are transferred from the valence band to the conduction band, and an equal number of holes are created in the valence band. Under the influence of an electric field, electrons and holes travel to the electrodes, where they result in a pulse that can be measured in outer circuit. Germanium detectors are mostly used for gamma spectroscopy in nuclear physics, as well as X-ray spectroscopy, while silicon detectors cannot be thicker than a few millimeters. Germanium can have a depleted sensitive thickness of centimeters, and therefore can be used as a total absorption detector for gamma rays up to few megaelectron volts. These detectors are also called high-purity germanium detectors and needs low temperature, 77 Kelvin. Cooling reduces thermal excitation of valence electrons so that only a gamma ray interaction can give an electron the energy necessary to cross the band gap and reach the conduction band. Using semiconductor detector, we can achieve a very good energy resolution, which make close gamma energies distinguishable. An example, you measure 500 microgray per hour gamma dose rate from an unshielded point-like iridium-192 source at a distance of 250 centimeters. Estimate the activity of the source. The gamma ray dose constant of this nuclide is given. Dose rate is inversely proportional to the square of the distance. Change the form of the formula, express the activity, and substitute the given numbers. Distance has to be measured in meter, hence we find also meter in the dimension of the dose constant. Value is given in gigabecquerel. Use the link below to make your daily work easier. This is retrocalculator.com. Thank you for your attention.
Okay, so Sila, first, are there any questions that Sila maybe can answer? Otherwise, we have to forward them to Mateo. Okay.
Do you receive any new information? Do you heard about these things before?
I did hear about them before because I already frequented a lecture. And also this is actually what I'm hoping I will be working with such equipment. So.
Okay. Yes, I think it was very useful. Mostly who are coming from as a master's student, you have to measure with these equipment, of course. But I think for the bachelors, for example, for the first and the second year bachelors, I think for them it's essential to know what to use in which situation. Okay, now Kirsten is break, and after that we will have a 2 video.
Yes, exactly. I was wondering, because it's already 41, shall we make a break until 12 o'clock and start or 10:55 and then start at 10:55?
Okay, 10:55. Good.
Yeah. Okay. So yeah, I'll announce this also in the chat. So we may make a break now until 10:55 and then we take up again at 10:55. Okay.
Okay. Okay.
Sila will inform David. I don't know whether he's still here with us, but maybe just give him a shout out.
No, I think no. He leave us. We will have two video. One from David. David sent me the video. I'm going to run it. It's connected to the presentation of yesterday and today. And we will have another video from Mate Lajos about the decontamination, the person mostly in the nuclear medicine situation.
Okay, good. So then we start at 10:55.
Okay.
Okay, see you all
Bye.
then. Bye.
Okay, maybe we can start. Are you coming back? Okay.
Okay.
After that, we will have a lot of shift.
Good. So you're sharing the video, huh?
Yeah. The first presentation, first laboratory presentation, I think that would be better to give from David. Now a little bit radiation protection after a little bit imaging to keep alive the group. And David made this video in his laboratory. It is a small homemade laboratory, a city laboratory. They build a small city, and now you can see how we receive the image from the city. Okay, I share my screen and we can start. Can you see?
Yes, we can see this.
Hi there. We are about to enter some air raid shelters just behind me. There we can find my CT scanner. So let's go inside. We came here down with the CT scanner in order to have all these concrete shielding all around. You can see how thick the concrete walls are, so you don't have to build extra shielding for your equipment. We are going to go inside and take a look at all of the equipment present. Just for a quick overview of the setup, you will see here the part where we are now. We are going to enter this room. You will find the CT scanner over there. There's going to be quite an important door here that we're going to see. So let's go inside. When I open this door, it's not only that happening, what normally happens when you open the door, that you can go inside, but there is also a small lock over there, and that lock disrupts the electricity every time it is open. So this is wired inside all the way through and to the X-ray source. So in case anyone enters the room and the X-ray source is on, it will disconnect. On one side of this setup, you can see an X-ray detector with scientific area somewhere around here, hosting something like 1200 times 1000 pixels, so very finely pixelated Texela panel. One pixel is approximately 70 micrometers by 70 micrometer large. You will see this object moving tablet. It's a very high precision moving tablet. If I just turn it, you start seeing rotating dinosaur plastic. Okay. So this rotating tablet can rotate one way, and you can see it's also a linear tablet, so you can move sideways your object. Nowadays, we only use the rotating part of this table for today's demonstration. Also, we will see that. On the other side, you will see the X-ray source. This X-ray source is going to emit the X-ray photons through this diode window, and it will go towards the object, and after the object, it will reach the detector. You also see here a computer governing the whole measurement. This computer is going to be responsible for switching on and off the X-ray source, for moving the tablet and to record the data. What you also see here is some high voltage sources, one for the detector, other one is for the X-ray tube. Now, in a normal machine, this setup would be different. You would have a rotating source and detector system revolving around your object. But now, you will have a rotating object and stationary source and detector. Just imagine that you have to give high voltage for your X-ray tube, and you have to be very speedy when getting all the acquired data signal from your detector. If you put that on a revolving rotary table, the so-called gantry, we are going to run into loads of engineering troubles. How to get all the data off from a rotating system, how to put the high voltage on a rotating system. It's not unsolvable, but it would cost a lot more. It would be really hard to do it in that circumstances. So now we deal with the easier one that is good for making CT scans, but it's not that good if you have a living organism. If you have to rotate a living organism, all the organs will be distorted. So it will not make a very nice scan of the living tissue as it deforms, as it turns, stuff like that. Okay, so that is a lab setup. What else would you need to operate such a machine? Well, that is radiation protection, quite important. I told you already, we have very big walls here, so you don't have to care about all the radiation going through walls. But there are not only walls here, there are also doors. One door, if you turn around, I'll do that again, so for you it's going to be useful. So I'm looking at the equipment. Now I'm turning myself on the spot, and you will see the door that I use. You can draw a straight line from the X-ray source to that door. So radiation scattering from an object may go through and leave this room through the door, through a wooden door. So for radiation protection measures, we have put extra lead on this door here. So now this lead layer can be seen somewhere here. And that is used now for protection, shielding of the radiation scattering from the object, going towards the door to the operation room where I'm going to be sitting in the next couple of minutes. Now I'm outside in the control room. In a remote desktop software, I logged into the computer inside, and now you can see the screen of that computer, and you can see the control user interface of the program that we wrote to put together this CP setup. What you can see here in this small box is the image that the X-ray detector creates for us. Now you see these vertical stripes. Those are just because the detector panel is not calibrated. In your camera, normally you get a calibration by the manufacturer, so you will see a totally smooth image. Here, every pixel has different sensitivity, so you see these vertical lines. Now what you see actually is just a single image I just took a minute ago. I now start making images, one after the other. Now the detector is set to 300 milliseconds. I will now make another setting just to show you that we 300 milliseconds. So 1/3 of a second approximately. And now I can start making images one after the other. Let's see what happens. You see now that there is a small vibration. How it is just because the detector power inlet is not fully stable. It is stable and stabilized, and in the right, so this image is just the black current image, the detector, not having any signal. Here you see a histogram, minimum and maximum. You see that the lowest pixel count is 200, so the black current signal is about 200. The maximum would be, and the maximum of this black current value is 700. And the total range that we are going to measure in is 16,000. So approximately 10% of that 16,000 is used for black current. And when you do a CT scanning, later you have to correct those images for this black current. What I'm doing with this image as well, I'm inverting it. It's quite usual for digital X-ray recording. Now, before we do any serious measurement, we have to take care of the radiation protection. And I told you how the setup was done. So now I will put the X-ray source in to full capacity, and say current up, energy up, and now check what the reading of the dosimeter says. Now you see some elevated dose levels, the X-ray source is on, and now I will go through very close to the door. And you start getting something like 5, 6, 7 microsieverts an hour. I come back to the position where I'm recording, so to the very special spot, and I will now switch off the X-ray source. And now you see that the radiation level goes back to normal. I did this measurement to show you that indeed the door I explained earlier is quite important to be open. What I did now, I closed it, just to show you that its importance is very, very high. Now I'm going to close it and redo the measurements. Now you see I switched on the X-ray source on full capacity, and I'll go to the same position as before. And you see now the reading does not increase. So indeed that door makes its job. I made it too easy for this radiation protection setup. What I do now is I put a jar of water into the line of the X-ray source, because this water is going to scatter the radiation. And now check whether that lead reinforced door can do its job and decrease the dose to levels acceptable for this measurement. So now the X-ray source is again on with a full bottle of water in the ray. And now let's take a look at the readings of my dosimeter. Now it has increased by the radiation coming through the walls actually, and but not much. And now I will put this dosimeter very close to the door. Now you see the previous values that we have measured a lot higher than putting it in the plastic bottle, but it does not reach the microsievert range that is that was before without the door being open. So indeed, when you put in the one bottle of water, you will see an increase in the radiation levels. It means it will really scatter all around the X-ray radiation, but the level is quite low. And if you have that door enforced with lead, you will not get any actually really serious radiation, but you can just detect if someone has switched on an X-ray source. So I see these images, but we don't have an X-ray source. Now I'm going to switch on the X-ray source. And that's what you see. Here is the control panel of the X-ray source. Here you will have the current, and here you will have the voltage. If I put down the voltage, you will see quite low contrast between air absorption and plastic absorption. Now I will put it to the official minimum, is 35 kilovolts. And then if I start increasing the current, you will get more and more photons out of the X-ray tube. So you will see actually more contrast between the background noise and this dinosaur or plastic skeleton. The image automatically scales itself. If I take that out, you will see basically nothing. So I will make a manual scaling and then increase the current. And then it still automatically scales. Very weird. Very weird. Oh, well, so it's not supposed to automatically scale. But now you can see this very nice dinosaur image. Well, it's very lifelike because they need to officially check on me, the pathogens, whether everything is okay and going fine with me, and it is going fine with me. Very good. So now we see the plastic skeleton of this dinosaur. And what I would like to show you as well is that we can turn it around. So now I started turning around the dinosaur. You perhaps see it as it rotates very slowly. Here, for example, at the thighs, you see that now you start seeing both of the legs. The thighs opening up. So indeed, you can turn around the object if you wish. Now what you see here is actually a professional throwing die. Now you can see it better. So it's a casino throwing dice. The special thing about it that the edges are not rounded down, but they have very sharp edges. I use this for getting the resolution out of the CT scanner. So it is quite well manufactured. So I'm using that as like a resolution photo. What I'm going to do, I'm going to put this in a glass of water, and then let's see what you get. Now you have the plastic die in the cup, and I will put now the X-ray source on and start the triggering. Now you have minimum, below minimum energy. Yeah, now you see here the plastic coffee cup, and this is the level of the water, and the cube is somewhere inside. Now I will start putting the energy higher and higher and higher. Now you will see more and more transmission as the energy level increases. Now you've got some saturated pixels around, and if I increase the current, again, we see higher and higher put through, more and more pixels saturating, and starts eating the very cup. I do it more and more and more, and what is quite visible that you can't see the cube. Although they are from different material, they have very similar densities and a very similar effective elemental number Z. So you can't really see it. So what I'm now going to do, I'll put in an aluminum tube into the same setup in the same filter. So now this is the aluminum tube. It is also manufactured to precision. It is exactly 1 centimeter on the sides, and it has better than 100 micron manufacturing precision. I also use this as a resolution phantom, and I'm going to put that in filter to see how that works. Now I switched on the X-ray source, and you see the plastic cup inside the filter, and there is basically not much transmission in the middle. So now I'll put the intensity to the highest possible, while being with the energy almost at the lowest margin. Now I'll start increasing the energy. And perhaps you start seeing here the small aluminum tube. Put the energy higher, and you see that the contrast becomes higher. In the middle, you still get black, so through the aluminum, not much of the radiation goes through. And in the histogram, you see those are the photons not going through the aluminum. Now start increasing the energy. You see that at the edges of the cup, you get more and more pixels saturated. It's still in the middle. The cup, the small aluminum dice does not pass through much radiation. So now I will go to the highest with the energy. Now you start seeing through the aluminum. Now what I did, I actually put this aluminum tube on top of the plastic die. So I will start rotating it, just for you to be sure that you can't see the plastic die, and you can see the aluminum die revolving around and around and around. So you see, there is basically no contrast between water and plastic, and there is much contrast between water and aluminum. One of the equipment vendor engineers used to say that living body tissue is basically water and aluminum, because the effective transmission of the human body is like water, and the bone transmission is something like aluminum. So basically, you do see something like living tissue contrast. If you replace plastic with water, nothing will happen. So you can make a phantom out of plastic or water, doesn't matter. It will behave almost the same. And if you put aluminum, then the density is higher, effective atomic number is higher. So you will start seeing this cube in the middle. So basically, that is what I wanted to show you as a demonstration how contrast is built in an X-ray machine. And for the last image to show is that the tablet is still revolving. What I did, I just emptied the water out of the cup, but not fully. So you can see it here in that paper cup. You have a bit of water. Then I have the plastic die, and on top I have the aluminum die, and it's revolving. So you can sort of see how that indeed there is the plastic cube there inside, but you can't see it through the water. And then you could see the aluminum die on the top, also in water, but now it's also very dramatic. But now you can also see the plastic. I will start increasing the intensity.
just before I start lose the cup sides, so you can still see the side of the cup. And then you can see that the transmission through the diagonals of the throwing die is bigger, and that in the aluminum that's quite not really enough to see through. But thank you for your attention of this laboratory exercise.
Okay, super. Sila, I think it's difficult to take questions here, I guess.
Yes, but I think most things David explained, and it is just some kind of verification of knowledge or give some image explanation. I think it whole together is okay, and I think that in this way it can be more understandable.
Okay.
If you have any question, yesterday I sent to you the email of David. If want today, I also can write here, and you can send him the email. Mostly he answered on the emails, but now he is very busy. Just I take here. Here is the email address, and the other case tomorrow they will have a new presentation about the MRI, but this presentation cannot give by David. It's given by his PhD student István Homoly, but he also can answer on any kind of questions, of course. Okay, and now we have one more. This video will be, just a minute, will be about the decontamination of radiation, mostly what we use, for example, in the medical field, the nuclear medicine, and in any case, it's very, very useful because it can save your health. And maybe not so interesting because it's better to organize than face to face, because in this case you can try to do this, but now we cannot organize face to face, and this is the reason that they make a video on this topic. But it's very, very useful, and take care about these things what you can see now here, because after in your work, if you work with the open sources, it would be very useful. Okay, I'm going to share my screen. Can you see?
Yeah.
Dear ladies and gentlemen, my name is Máté Lajos. I am physicist, and I would like to present you decontamination today. As beginning, I have to share you some basic information in connection to decontamination and some definition as well, in order to clarify the meaning and share a good practice. In the framework of radiation protection, the contamination always means contamination with radioactive substances, radioactive materials. What can be contaminated? Everything. Tables, skin, even radioactive materials, or radioactive material containing devices and dosage meters also. We call the situation surface contamination, and the use unit for characterizing that is the becquerel per square meter for a given radionuclide. Sometimes we only measure CPS, which is the abbreviation of count per second, or CPM, count per minute. Step a little bit further from the topic and have a look at the type of exposures. If you are affected to ionizing radiation, it can be external and internal exposure. Start with external radiation. We make differences between alpha, beta, and gamma radiation based on their range, free path lengths in the air. The most dangerous are neutron and photon radiation, X-ray gammas, because they have no electric charge, so they affect several meters away. Beta particles' free path length in the air is less than 1 meter, energy depending, and the less dangerous is alpha particle because it attenuates in some centimeter in the air. The protection from external ionizing radiation has three main forms. They are time protection, distance protection, and application of shielding materials. The less time you spend near the source, the less dose you receive. The greater distance you keep from the source, the less dose you receive, and using appropriate shielding material, you will be less exposed. Using appropriate material for shielding is important. The used shielding material depends on the type and energy of the radiation. For example, lead shielding materials with high atomic number shields gamma and X-ray effective. Beta particles can be stopped by a layer of plastic. Alpha particles can be stopped by a sheet of paper or even by your skin. Radiation exposure occurs when all or part of the body absorbs penetrating ionizing radiation from an external radiation source. Exposure from an external source stops when a person leaves the area of the source is shielded completely, or the process causing exposure ceases. An individual exposed only to an external source of radiation is not radioactive or contaminated and may be approached without risk, just like after a chest X-ray or CT scan. Radiation from external exposure alone is either absorbed without the body becoming radioactive, or it can pass through the body completely. Therefore, if a person is scanned with a radiation survey monitor after external exposure alone, the device will not register radiation above the background level. Internal radiation is caused by radioactive material in human body, which takes part in metabolic processes. Radioactive contamination, mainly internal radioactive contamination, can cause internal radiation. Let us speak about radioactive contamination. Contamination results when a radioisotope, as gas, liquid, or solid, is released to the environment and then ingested, inhaled, or deposited on the body surface or on any surface. We have to make difference between external and internal contamination. First, external contamination. External contamination results when radioactive material is deposited on skin, hair, eyes, or other external structures, much like mud or dust. External contamination stops when the material is removed by shedding contaminated clothes and completely washing off the contamination. How to diagnose? We have to scan the suspicious surface with appropriate radiation survey meter. We have to apply shielding against the spreading radioactive material, for example, stay in closed place in house, or wearing whole body covering protective clothes, gloves, and so on. Shielding blocks radioactive material from covering the entire person. Make it clear, we protect ourselves not against ionizing radiation, only against radioactive materials depositing on our skin or clothes. Some words about wound contamination. With explosion of a radiological dispersal device, dirty bomb, radioactive shrapnel or fragments can be propelled through the air and become embedded under the skin or in tissues or organs. Radioactive material can enter the bloodstream or the lymphatics. This is internal contamination. These fragments must be removed with special care. So, if our body is injured, we mustn't work with unsealed sources, for example, in an isotope laboratory. This would increase the possibility of the internal exposure. So, what is internal contamination? Radiation exposure also occurs after internal contamination, for example, when a radionuclide is ingested, inhaled, or absorbed into the bloodstream. Have a look at the internal contamination via respiratory tract. When aerosol particles are inhaled, smaller particles can reach the alveoli, whereas larger particles will remain in proximal airways. Tiny particles can be absorbed by the lymphatic system or the bloodstream, or continue to irradiate locally. until expelled, removed, or depleted of their radioactivity. Have a look at the internal contamination via digestive tract. If swallowed, soluble radionuclides may be absorbed in the upper tract, whereas insoluble radioactive particles may affect the lower gastrointestinal tract. Depending on the specific radioisotope, particles in the gastrointestinal tract may be debauched, expelled, or removed using drugs. Last one is called decorporation. Have a look at the internal contamination via radioactive dust in open wounds. Smaller radioactive particles in open wounds may be absorbed into the body via blood or lymphatic channels. This kind of exposure stops only if the radionuclide is totally eliminated from the body with or without treatment. As a summary, internal contamination results when radioactive material is taken into the body via inhalation or ingestion or open wounds. Internal deposition of radioisotopes in organs results in local exposure at that location. Internal contamination continues until the radioactive material decays, is flushed from the body by natural processes, or is removed by medical countermeasures. How to diagnose? If after external decontamination, an appropriate radiation survey meter continues to identify significant residual radioactivity, suspect internal contamination. Collect spot urine sample from isotope measurements. Make instructions for sample collection, labeling, packaging, and shipping. Consider total body radiation survey with modified hospital nuclear medicine equipment or with whole body counter. If the contaminating radionuclide has no measurable gamma radiation, the whole body counter, accurate germanium detector, cannot detect the radiation. Measurement of urine, blood, excretories have to be analyzed then. Have a look at the incorporation. After inhalation, ingestion, or wound contamination, small radioisotope particles may be transported via blood or lymphatic into cells, tissues, and organs. Isotopes can be alpha, beta, or gamma emitting radionuclides. Most dangerous are alpha emitting radionuclides because they transfer all of their energy to the nearest tissues. Radioisotopes can be incorporated into one or more organs specific for that chemical element, for example, thyroid, lungs, kidneys, bones, and so on, resulting exposure at that site. Medical countermeasures called decorporation agents or other procedures, for example, diuresis, may be needed to remove radioisotopes that have been incorporated into tissues. Toxic effects of radioisotopes may be due to their chemical and radiological properties. Decorporation is also a toxic effect because decorporating drugs are not specific for the radionuclide, but specific for the chemical elements, and usually the chemical elements with similar electron fields. What to do in case of an emergency? Don't panic. First step is life-saving, first aid, so giving help to the sick or injured person until full medical treatment is available. Once we are convinced that the person is alive and not in danger of death, we can start with radiation protection issues. In this situation, my colleague, Mr. David Mihai, helps us to illustrate an accident happened in an isotope laboratory. I prepared with some demonstrating tools, a special liquid emitting UV photons, and a handheld detector which detects these UV photons, similar to a surface contamination measuring instrument. We are wearing whole body covering working clothes, gloves, mask, helmet on the head against spatter of radioactive material. Let me introduce my colleague, David Mihai, who helps us to illustrate this accident in an isotope laboratory. Welcome, David.
Hi, everyone.
David will wear this artificial bond. He was working in an isotope laboratory with well-measurable beta-emitter radionuclide when an accident happened. David is wearing whole body covering, working clothes, gloves. Suppose that he is wearing mask and helmet on the head against spatter of radioactive material. He is wearing personal dosimeter. He alone cannot prevent the accident, cannot make the decontamination, so we need a second person who does it. What happened, David?
I was working with strontium-90 isotope when I fell and injured. Not only my gloves, but also my skin was injured.
Now I'm making the open bond visible. Imitating the surface contamination, we use this special liquid as a radioactive material. Of course, it is not radioactive, only emits UV photons. We have a measurement device belonging to that liquid. It measures count per second and has audible beep signal. The sensitive detecting surface is covered with a thin, replaceable plastic layer in order to prevent the device against contamination. Now I am contaminating David's bond, and we will decontaminate using our prepared decontamination kit. Now it is visible, yellow liquid. It is a lucky situation, but radioactive materials not usually visible. Start the checking of the injured person. David is not in danger of death. We can communicate with him. We see his bleeding wound, but do not start to decontaminate that, because we have to check previously whether he inhaled or swallowed the radioactive material. He did not incorporate via this tract because he was wearing protective tools. Now we can carry on with the open bond. Using our counter, we establish external radioactive contamination. Protection of nuclear instrument is crucial. With contaminated instrument, you always have relative high signals, but false signals. So you cannot determine the purity of the investigated surface. Use a thin plastic coverage to prevent the contamination of the sensitive area of the device. Of course, you reduce the sensitivity of the detector, but you only have to determine whether the surface is contaminated or not. The value is not important in the first steps. We have to prevent or reduce internal contamination. I remove his gloves. Now I became also potentially contaminated. I start washing his wound with physiological saline. We collect the washing liquid and radioactive waste in order to estimate the amount of the incorporated radioactive material. We know the amount in becquerel of the used radioactive material. We collect and measure the rest, and the subtraction is assumed as incorporated. We are washing and pressing the wound area. Thus, we try to remove the potentially contaminated blood from the nearest tissues. When we finished, we check the radioactivity on the wound with our counter. Hopefully, we measure less counts per second, and we have to carry out a control measurement on the tray. The most radioactivity was washed out and collected on the tray. Check the wound again, slowly, with your instrument. Give enough time to the instrument to be able to detect the possible radioactive substance on the wound. Try to measure as close to the wound as possible, but pay attention not to contaminate the instrument. If we could not remove the whole contamination from the area of the wound, we have to use cotton and tweezers. Pick up the cotton ball with your tweezers and start to wipe the dirt from the wound from the inside out. Pay attention to rotate the tweezers while wiping so that the new uncontaminated surface of the cotton ball always touches the new skin surface to be cleaned. The contaminated part of the cotton ball mustn't touch the wound again. Do not use the contaminated cotton ball again. What to do with that? It is a sample to measure the activity collected from the surface of the skin or wound. The collected radioactive material did not cause internal contamination, so you reduce the internal exposure of the injured person. Pay attention again. The used cotton, tweezers, your hand, hopefully only your gloves, became potentially radioactive. Do not touch anything with your contaminated gloves because you make that object also contaminated. So later you have to decontaminate more and more objects in your laboratory. This advice also relates to your handheld nuclear instruments. How to solve this situation? You need a third person who is responsible for carrying out surface contamination measurements. He or she checks with this counter the cleaned or contaminated surfaces, holds prepared sample holder, and does not touch anything in the laboratory. If you have no third person who carries out these measurements, you have to use fixed, not handheld instrument. The collected sample, the cotton ball, has to be placed in a prepared sample holder, plastic bag. Third person has to assist closing the collected samples. Use big plastic bags and prevent to touch the external surface of the bag with the used cotton ball. The third person's hands only touch the external surface of the bag. The radioactive cotton only touches the internal surface of the plastic bag, so the radioactivity is inside of the bag. Close that. Label the prepared sample holder with number, origin, and time. Time is important if you decontaminate radioactive material with low half-life. It decays fastly. When the sample will be measured some hours later, the measured activity will be less than we collected from the wound. So we have to calculate the activity to the time of the accident. We know the amount in becquerel of the used radioactive material. We collect and measure the rest, and the subtraction is assumed as incorporated. Low half-life leads to another piece of advice. If you contaminated a room, not human body, with low half-life radioactive material, you have to optimize the prevention. If you do not need this room for a period of time, or you can remanage your work, I suggest to wait until the radioactive material decays. After it has decayed or the activity reduced to an acceptable level, you can decontaminate the rest. So you protect yourself from a high external and a potential internal exposure. After the radioactive substance is removed from the open wound, we check the whole body, mainly gloves, and the undersurface of the person's shoes. Finishing your work, take special care for taking off your gloves. The external surface of your gloves is contaminated with radioactive material. The internal surface is not contaminated, so your skin is not contaminated. Lift up the left glove from your left hand using your 2 fingers in gloves, right hand, and twist your left glove. Do not touch your ungloved left hand with your right hand in glove. Remove your right glove, also touching only the internal surface with your clean left hand fingers. Internal side of the right glove can be touched with your clean left hand. Thank you for your attention.
Thank you for your attention.
Okay, that's all for today for the medical field, and now the quiz.
Okay, so as I said, it was just an explanation. Okay, so then we simply stop now until 12 o'clock, and then at 12 o'clock we will have the quiz for today, for the medical quiz for today. Okay, shall we do this? Yeah. Okay. See you at 12 then.
So here we are. I saw that already almost 18 participants registered to the quiz session, the final quiz session for medical physics lesson. I send you again the link for them to maybe didn't see it or logged out later. Just one second. I'm going to share in the chat. If I'm right, we should have today almost 27 participants to the quiz. Okay, more people is coming. 21. Let's wait a bit more, and then I go on sharing my screen. But again, as you know, I invite you to follow your own screen and the link I send you. I'll share only for Zoom and for the recording the screen. So there are 3 or 4 participants missing yet. I will wait 1 minute more and then we could start, I think. In the meantime, I invite you to join, obviously, tomorrow morning, last session about medical physics. And also, I remind you that in the afternoon at 5 o'clock tomorrow, we will have the event career guidance. So we will host several experts and professionals from different fields in the nuclear sector that will be able to give you information and to explain you which opportunities the different sector of the nuclear can offer you. So I warmly invite you to join. It will be a very interesting roundtable, and you will be able also to interact and to ask them for information, question, whatever you want. So the final results will be published the last day for the closing ceremony, as Bojdar asked. So today we will see again the final results for today's session. Then I'm going to calculate the final sum for both medical physics and nuclear energy, and then the final result will be published only the last day on Friday during the award and the closing ceremony. So you have to wait a bit. I think we are all ready to start. No more people is joining, and I suppose we can start. If not, it could be quite late. Okay, I'm going to share my screen and to start the quiz. Okay, here we are. So we are ready to start our last quiz for the medical. This is the chat. I'm sorry. Should we send finish project? Okay, I leave Xila to reply you in the chat. Meanwhile, we can start with the quiz. So the countdown is starting now for the first question. So watching this picture, as Professor Lagradi explained, what is now a wave in this picture? Is a bit tricky question, but it's easy. If you watch this picture as Professor explained this morning, what is now a wave? So everyone has voted. And no, in this case, watching the picture, the wave represented by dolphins. So the correct answer was the last one. Second question. Question number 2. How would you filter an image using the Fourier transform? First, multiply by the Fourier Lagrangian and take the square root. Fourier transform the image, multiply by a function and transform back. Filter the Fourier transform into an image support, or Fourier transform the image and multiply by a filter. Few seconds left. And the correct answer, yes, it is the second one. Congratulations. Fourier transform the image, multiply by a function, transform back. Let's move to the next question. Question number 3. Always 25 seconds to answer. What is a sinogram? As we saw this morning, a sinogram is the radian transformation for a polar Fourier transform. Fourier transform to 2D wave function, line integral of a 2D function, or medical imaging name with a sine wave. 10 seconds left. Time is up. Everyone is voted. And the correct is the line integral of a 2D function. Let's move to the question number 4. How does filtered back projection inverse radian transformation work? Sinogram is filtered in Fourier space, project back to image space. Sinogram is Fourier transform, project back to filter image space. The sinogram is projected into Fourier filter space and back. The sinogram is Fourier and inverse Fourier transform. So the correct answer is the first one. The sinogram is filtered in Fourier space, project back to image space. Next question. What is the maximum likelihood expectation maximization method? Likelihood estimation of the highest probability expectation, estimation of the most likely maximum isotope concentration, estimation of the most likely isotope concentration of the expected maximum iteration of likelihood of isotopes. Everyone has voted, and exactly is the third one, the estimation of the most likely isotope concentration. Congratulations. Let's move to the question number 6. So how would you generally produce a positron decaying isotope? By bombarding element with gammas, by bombarding element with neutrons, by bombarding element with positrons, or by bombarding element with deltas, or supporting spring field isotopes. Few seconds left. And yes, it's by bombarding elements with positrons. Answer number 3 is correct. Question number 7. What is a FDG? An FDG is a filament drugs for glucose tomography, functional diagnostic glucose, fluor diagnostic glucose, or fluor desoxyglucose. Time is up. And the correct answer, yes, exactly, it's the last one, fluor desoxyglucose. Next. What is the characteristic energy of gammas at PET measurement? So it's 1022 megaelectron volt, 511 megaelectron volt, 500 kilo electron volt, or 1022 kilo electron volt. Let's see the correct answer. Yes, congratulations. Is the third. It's 511 kilo electron volt. Let's move on to the question number 9. How would you detect spatial information with scintillation crystals? By weighting signals of photomultipliers attached to the same crystal, by connecting multiple crystals to the photomultiplier simultaneously, by putting separate photomultipliers to each of the crystals, or by filtering the energy response of the scintillators. Few seconds left, and still some answer is missing. Okay, time is up, and congratulations again. The correct is the first one, by weighting signals of photomultipliers attached to the same crystal. Question number 10. We move to the half of this quiz. What is a collimator used for? Collimator is used for collimating the beam to achieve better noise, for collimating the photomultipliers, for creating the separation of line of responses, or for weighting the camera top to prevent toppling. Okay, everyone is voted, I suppose, yes. And the correct answer is the third one, for creating the separation of the line of responses. Congratulations. Question number 11, sorry. What color are gamma rays? Gray, dark blue, green, or no color, they are invisible. Oh, quick answers, I see. Few left. Time is up. And yeah, they are no color because they are invisible. Let's move to the next question. After shut down the X-ray machine, the ionizing radiation stops in 10-30 seconds, in 1 hour till the machine became cold, immediately, or a few years later when the radioactive elements decay. So we are moving to another topic, radiation and radiation protection, in the second half of today's quiz. Few seconds left and still one answer missing. Time is up, and the correct answer is the third one, because the ionizing radiation stops immediately. Question number 13. Which is the symbol of radiation hazard, radioactive material ionizing radiation? So A, B, C, D. In the order you can see them, the picture, maybe they are a bit small, but the first is the A, the second the B, the third is the C, and the last one is the D. Everyone has voted, and yes, exactly is the second one. Question 14. How can we detect ionizing radiation? Only with radiation detectors. Using its heat effect, it illuminates light, or it destroys living organisms. Ten seconds left, even less. Time is up, everyone is voted, and yes, the correct answer is the first one, only with radiation detectors. Question 15. What do we measure with nuclear detectors? The dose rate, biological hazard, the amount of radioactive material, or the temperature of the radioactivity? Okay, everyone has voted, and yes, the correct is the first one, the dose rate. Next question. Order the types of radiation, starting with the less dangerous, considered as external source. So alpha beta gamma, gamma beta alpha, gamma alpha beta, or beta alpha gamma. The less starting from the less dangerous, considered as external source. Yes, exactly, is the first one, alpha, beta, and then gamma radiation. Next. Other types of radiation start with the less dangerous, but now considered as an internal source. And you have the same option here. But now considering them as internal source. Yes, exactly, is the opposite, so it's gamma, beta, and alpha. Next, the question left, number 18. A worker was affected to high external gamma radiation. Which instrument will you use to determine the exposure of the worker? Personal dosimeter after the exposure, whole body counter, and measurement of urine, blood, and excretories, ion chamber, or none of the above? Everyone has voted, and the correct is the last one. None of these instruments will be helpful to you to determine the exposure of the worker. 19. You are decontaminating a person in open wound. How do you protect yourself against internal exposure? using lidded shielding, for example, apron, glasses, and gloves, use personal protective tools, protective clothes and gloves, etc. Wear operative personal dosimeter or time, distance, protection, and application of shielding materials. Everyone is voted. And yes, the correct is the second one. Congratulations, using personal protective tools. Last question, now you'll have a bit more time. So this is the introduction. You discover an unconscious worker in the isotope laboratory who worked with liquid radioactive material. Files are broken, radioactive material are on the floor, and the worker has bleeding wound. Now you have to order these steps to do, and you will have 35 seconds to do it. So the steps are the check worker is alive, first aid, determine and isolate the radioactive contamination on the floor, decontaminate the open wound, or decontaminate the floor. You have to order these steps. Two seconds left. Okay, time is up. Everyone is voted, and yes, congratulations. The correct steps to do are the third. So check worker is alive, first aid, then decontaminate the open wound, then determine and isolate the radioactive contamination on the floor, and finally decontaminate the floor. Now we are going to see the leaderboard for today. I highlight again, they are the results only for today's quiz, not the final results. We are going to see it only the last day, Friday, during the closing ceremony and awards. So let's see the leaderboard for today's quiz. And congratulations to Božidar for the first place today, and to all participants. So first place for Božidar today, then Luca and Tobias. So the quiz for the medical physics are over. I hope you enjoyed them. And now I'm stopping sharing my screen, and then we can move to the end of today's session. So Kirsten, if you want to say something more.
Well, I can say something more. I thought Sila wanted to jump in for a last word.
I hope that you enjoy this day and you learn much more, and see you tomorrow.
Okay, so and you will share the information. Presentations will be shared if the presenters agree with it, and yeah, and you will be in contact by email, and then give a link to it.
Is the video will be available in the ENS YouTube channel? Because in this case we cannot share because there is everything, no?
Yes, the video of the sessions will remain available in the ENS YouTube channel.
Yes. Yeah, but instead of I am going to ask the lecturers, and I will share in the drive, but not today, maybe on Friday afternoon, because until that we have a lot of other works.
Okay, super. Good. So we close for today, and as Matja said, tomorrow we'll still have some medical questions, and then but this afternoon Matja will take over, and we talk about nuclear energy. So, and then have a good lunch break, and see you tomorrow, or see you this afternoon if you follow both sections. Okay, talk to you soon. Bye.
Bye.
Thank you. Goodbye.
Thank you. Goodbye.